The universe is stretching faster than the speed of light. It's a fact so staggering, it almost feels like science fiction. Picture the cosmos as an ever-expanding rubber band, galaxies racing away from each other as if pulled by invisible hands. But what's really driving this cosmic push, and why does it matter to us? Here on this tiny blue dot in the vastness of space, the answers lie in forces so mysterious, they challenge everything we think we know about the universe. From the enigmatic pull of dark energy to the relentless tug of gravity, the story of universal expansion is one of the greatest puzzles in science, one that holds the key to understanding the ultimate fate of the cosmos. Could this expansion ever slow down or even stop? What does it mean for the future of galaxies, stars, and even humanity itself? In this video, we'll dive into the heart of these questions, unraveling the secrets of dark energy, the echoes of the Big Bang, and the forces shaping the universe. Together, let's explore the unknown and uncover the mysteries of the cosmic push. 13.8 billion years ago, everything we know, every star, every galaxy, every atom, was compressed into an unimaginably small, hot, and dense point. Then, in an instant, it all burst forth. This is the Big Bang, the moment when the universe as we know it began. Imagine the sheer energy of that explosion, a cosmic fireball expanding faster than the speed of light, filling the void with matter, radiation, and the building blocks of everything we see today. It wasn't an explosion into space, it was the birth of space itself, stretching and growing like a balloon inflating in every direction. But how do we know this actually happened? The answer lies in a faint, ancient glow that still permeates the universe, the cosmic microwave background radiation. Think of it as the universe's first photograph, taken just 380,000 years after the Big Bang. This afterglow, discovered in the 1960s, is like a snapshot of the cosmos in its infancy, revealing the seeds of galaxies and the early ripples of structure that would eventually give rise to stars, planets, and us. It's the most compelling evidence we have that the Big Bang wasn't just a theory, it was the spark that set everything in motion. The Big Bang didn't just create the universe, it set the stage for everything that followed. The initial burst of expansion laid the groundwork for gravity to pull matter together, forming galaxies and clusters, while also creating the conditions for mysterious forces like dark energy to emerge. But even as we piece together this incredible story, new questions arise. What triggered the Big Bang in the first place? What came before it? And what happened in those first fleeting moments when the laws of physics as we know them didn't yet apply? These are the mysteries that keep scientists searching, and they are the questions that will take us deeper into the heart of the cosmic push. As the universe expanded, scientists expected gravity, the force that pulls galaxies together, to gradually slow everything down. But in the late 1990s, something unexpected happened. Researchers studying distant supernova, the explosive deaths of massive stars, noticed something strange. These cosmic fireworks, billions of light years away, appeared dimmer than they should have been. Instead of slowing down, the universe's expansion was speeding up. This discovery was like finding a car rolling uphill without an engine. It defied all logic. The culprit, a mysterious force we now call dark energy. Dark energy is unlike anything we've ever encountered. It's not a substance or a particle. It's more like a property of space itself, an invisible push that counteracts gravity's pull. Imagine blowing up a balloon with tiny dots on its surface. As the balloon expands, the dots move farther apart. Now, imagine if the balloon started inflating faster and faster on its own, as if some unseen force were at work. That's dark energy, a cosmic accelerant driving galaxies apart at an ever-increasing rate. What makes dark energy even more baffling is its sheer dominance. It makes up about 68% of the universe's total energy content, dwarfing everything else, including the matter we can see and touch. Yet, despite its overwhelming presence, it remains invisible, detectable only through its effects on the cosmos. Could it be a fundamental property of space, woven into the fabric of the universe, or is it something entirely beyond our current understanding? The discovery of dark energy has reshaped our view of the cosmos, but it's also left us with more questions than answers. Why does it exist? How does it work? And what does its relentless push mean for the future of the universe? These are the puzzles that drive astronomers and physicists today as they peer deeper into the cosmos, searching for clues hidden in the light of distant stars and galaxies. The quest to understand dark energy is far from over. It's a journey into the unknown, where every answer leads to even more profound mysteries. In the vast cosmic arena, two titans are locked in an eternal struggle, shaping the fate of the universe itself. On one side, there's gravity, the relentless force that pulls matter together, binding stars into galaxies and planets into solar systems. On the other, dark energy, the mysterious, invisible push that stretches space itself, driving galaxies apart at an ever-increasing pace. It's a cosmic tug-of-war, with the universe itself as the rope. Picture this: gravity is like a giant hand, gathering matter into clusters, pulling galaxies into superclusters, and holding everything in place. On small scales, gravity is the undisputed champion. It's the reason Earth orbits the Sun, why galaxies spin, and why you don't float off into space. But zoom out far enough, and the balance shifts. Dark energy takes the lead, acting like an unstoppable force that stretches the fabric of space, pushing galaxies away from each other faster and faster. This cosmic dance is written across the universe itself. Look at the large-scale structure, and you'll see galaxies forming intricate webs, filaments, and voids. These patterns are the fingerprints of gravity's influence, pulling matter into dense clusters over billions of years. Yet, between these clusters, dark energy reigns supreme, creating vast expanses of emptiness as it accelerates the expansion of space. So, what happens when these two forces collide? On smaller scales, gravity wins. Galaxies like our Milky Way hold together, with stars and planets orbiting in harmony. But on the grandest scales, dark energy dominates, spreading galaxies apart like dots on an inflating balloon. It's a delicate balance, one that has shaped the universe as we know it. But here's the lingering question: will this balance last forever? Could gravity ever regain the upper hand? Or will dark energy continue to drive the universe toward an ever more distant future? The answer lies in the hidden depths of the cosmos, waiting to be uncovered. Now, let's turn our attention to one of the most critical tools in understanding the universe's expansion, the Hubble Constant. Named after the pioneering astronomer Edwin Hubble, this constant represents the rate at which the universe is stretching. But how did we come to measure something as vast and abstract as the expansion of the cosmos? The story begins with a simple yet profound observation. Light from distant galaxies isn't just moving away from us, it's being stretched as it travels through expanding space. In the 1920s, Edwin Hubble made a groundbreaking discovery. By studying the light from galaxies, he noticed something peculiar. The farther away a galaxy was, the more its light appeared shifted toward the red end of the spectrum. This phenomenon, known as redshift, was a direct clue that galaxies were moving away from us and each other. Hubble realized that this redshift wasn't random, it followed a pattern. The greater the distance to a galaxy, the faster it seemed to be receding. This relationship, now known as Hubble's law, laid the foundation for the Hubble Constant, the number that quantifies how quickly the universe is expanding. But measuring the Hubble Constant isn't as straightforward as it sounds. To calculate it, astronomers need to know two things: how fast a galaxy is moving away from us and how far away it is. The first part is relatively simple. Redshift gives us the speed. The second part, determining distance, is where things get tricky. Enter Cepheid variable stars, the cosmic lighthouses of the universe. These stars pulse in brightness at a rate directly tied to their intrinsic luminosity, allowing astronomers to measure their distance with remarkable precision. By observing Cepheid stars in nearby galaxies, scientists can calibrate the cosmic distance ladder, a step-by-step method for measuring increasingly distant objects. Supernova, the explosive deaths of massive stars, also play a crucial role. Type Ia supernova in particular are like cosmic flashbulbs. They all explode with roughly the same brightness, making them ideal, standard candles for measuring distances across vast stretches of space. By combining observations of Cepheid stars and supernova, astronomers have refined their calculations of the Hubble constant, painting a clearer picture of the universe's expansion rate. Yet, even with these advanced tools, there's a catch. Different methods of measuring the Hubble constant have produced slightly different values, sparking a heated debate among scientists. Some measurements, based on the cosmic microwave background, the afterglow of the Big Bang, suggest a slower expansion rate. Others, derived from observations of nearby galaxies and supernova, point to a faster rate. This discrepancy, known as the Hubble tension, has become one of the most intriguing puzzles in modern cosmology. Could it be a sign that our understanding of the universe is incomplete? Or might it hint at new physics waiting to be discovered? The implications of this debate are profound. The Hubble constant isn't just a number, it's a key to unlocking the universe's history and future. A faster expansion rate could mean that dark energy is stronger than we thought, accelerating the universe's growth more rapidly. A slower rate might suggest that our models of the cosmos need revisiting. Either way, resolving this tension could reshape our understanding of the forces at work in the universe, from the smallest particles to the largest structures. As scientists continue to refine their measurements and explore new methods, the Hubble constant remains a beacon guiding our exploration of the cosmos. It's a reminder that even the most fundamental questions, like how fast the universe is growing, are still open to discovery, inviting us to dig deeper into the mysteries of space and time. The universe's ultimate fate is one of the most profound questions in science, and the answer hinges on the delicate balance between dark energy and gravity. Will the cosmos continue to expand forever, or will it collapse back in on itself? Or could something even more dramatic lie ahead? Scientists have explored three primary scenarios, each painting a vastly different picture of how everything might end: the Big Freeze, the Big Crunch, and the Big Rip. Let's take a closer look at each possibility and what they mean for the future of existence itself. First, there's the Big Freeze, a chilling vision of a universe that never stops expanding. In this scenario, dark energy's relentless push continues to accelerate the cosmos, stretching space farther and farther apart. Over trillions of years, galaxies will drift beyond the horizon of visibility, leaving every star system isolated in an ever-darkening void. Stars will burn out, black holes will evaporate, and the universe will grow colder and darker until it reaches a state of near-perfect stillness. The Big Freeze isn't an explosive end, it's a slow, silent fade into obscurity, where even time itself may lose meaning. It's a scenario that feels almost poetic in its inevitability, a quiet final act for a universe that began with a bang. But what if gravity gets the last laugh? That's where the big crunch comes in. In this scenario, the expansion of the universe eventually slows and reverses, pulled back by the collective gravitational tug of all the matter within it. Imagine the cosmic balloon deflating, galaxies rushing toward each other as space contracts. Over billions of years, everything would collapse into an unimaginably dense singularity, a mirror image of the Big Bang. Some theorists even suggest that this could trigger a new Big Bang, creating a cyclical universe that endlessly expands and contracts. The Big Crunch offers a sense of cosmic symmetry, a dramatic return to the beginning, but it also raises questions. Would time itself reverse, and what would happen to the laws of physics in such extreme conditions? Then there's the Big Rip, the most violent and apocalyptic of the three. In this scenario, dark energy doesn't just accelerate the universe's expansion, it grows stronger over time, eventually overpowering every force that holds matter together. First, galaxies would be torn apart, then stars, planets, and even atoms. Space itself would unravel, leaving behind a fragmented, chaotic void. The Big Rip is a cosmic doomsday, an end so sudden and catastrophic that it defies imagination. It's a stark reminder of the raw power of dark energy and the fragility of everything we know. So, which of these scenarios is most likely? The truth is, we don't know yet. The fate of the universe depends on the nature of dark energy, a force we still barely understand. Is it constant, or does it change over time? Could it weaken, allowing gravity to take over, or will it grow stronger, leading to the Big Rip? These are the questions that keep cosmologists awake at night, driving them to peer deeper into the cosmos for answers. What we do know is that the universe's destiny is written in the interplay of these two forces, gravity and dark energy, and the story they tell will shape everything, from the largest galaxies to the smallest particles. The search for that story is far from over, and every discovery brings us closer to understanding the ultimate fate of the cosmos. Just moments after the Big Bang, the universe experienced something extraordinary, a growth spurt so rapid, it's almost impossible to comprehend. This is the theory of cosmic inflation, a brief but explosive period when the cosmos expanded faster than the speed of light, doubling in size countless times within a fraction of a second. Think of it like blowing up a balloon. At first, it's small and crumpled, but with a sudden burst of air, it expands into its full, smooth shape. That's what happened to the universe during inflation. It went from a tiny, chaotic point to a vast, smooth expanse in the blink of an eye. But why do scientists believe this happened? The answer lies in two mysteries that plagued cosmology for decades: the horizon problem and the flatness problem. The horizon problem asks why the universe looks so uniform. If you look in opposite directions, the cosmic microwave background, the afterglow of the Big Bang, is almost identical in temperature. But how could regions so far apart have reached the same temperature if they were never in contact? Inflation solves this by suggesting that these regions were once close together before being stretched apart faster than light could travel, preserving their uniformity. Then there's the flatness problem. The universe appears remarkably flat on large scales, meaning it doesn't curve back on itself like a sphere. For this to happen, the density of the universe had to be incredibly fine-tuned at the moment of the Big Bang. Inflation explains this by saying the rapid expansion smoothed out any curvature, like stretching a crumpled sheet of paper until it becomes flat. The evidence for inflation is etched into the cosmic microwave background itself. Tiny fluctuations in this ancient light, discovered by satellites like Cobe and Planck, match predictions made by inflation theory. These fluctuations are like fingerprints, revealing the seeds of structure that would later grow into galaxies and stars. It's as if the universe left us a message from its earliest moments, one that scientists are still decoding today. What's fascinating is how cosmic inflation ties into the universe's current expansion. Just as the early universe stretched exponentially, dark energy is now driving a similar, though slower, expansion on a cosmic scale. Could inflation and dark energy be two sides of the same coin? Some scientists think so, suggesting that understanding one might shed light on the other. But for now, inflation remains one of the most compelling chapters in the story of the cosmos, a moment when the universe transformed itself in ways we're only beginning to grasp. And as we explore its implications, we're reminded that the universe's secrets are often hidden in its most fleeting moments. As we peel back the layers of the universe's history, we find that the seeds of everything we see today were planted in the tiniest of moments, mere instants after the Big Bang. But these seeds weren't random. They were born from the strange and unpredictable world of quantum mechanics. At scales so small they're almost unimaginable, particles pop in and out of existence, creating ripples in the fabric of reality itself. These are quantum fluctuations, and in the early universe, they played a pivotal role in shaping the cosmos as we know it. Picture the universe in its infancy, a seething, chaotic sea of energy and particles. In this maelstrom, quantum fluctuations created tiny variations in density regions where matter was slightly more or less concentrated. These variations might seem insignificant, but when cosmic inflation kicked in, they were stretched to enormous scales. What began as microscopic ripples became the foundation for the vast cosmic web of galaxies and galaxy clusters we observe today. It's as if the universe took a whisper and turned it into a roar. The beauty of this process lies in its simplicity. Quantum fluctuations are a natural consequence of the uncertainty principle, a cornerstone of quantum mechanics. This principle tells us that at the smallest scales, nothing is ever perfectly still or perfectly uniform. Particles and energy are constantly in motion, creating a kind of cosmic static. In the early universe, this static was imprinted onto the fabric of space-time, frozen in place by the rapid expansion of inflation. Over billions of years, gravity amplified these tiny differences, pulling matter together to form the first stars, galaxies, and eventually, the intricate structures we see in the night sky. What's truly remarkable is how quantum mechanics, a theory designed to explain the behavior of atoms and particles, holds the key to understanding the universe on the grandest scales. The same rules that govern electrons and photons also shape the distribution of galaxies across billions of light years. This interplay between the very small and the very large is one of the most profound insights in modern cosmology, revealing a deep connection between the microscopic and the cosmic. Yet, for all we've learned, quantum fluctuations also hint at deeper mysteries. Why did some regions of the universe end up with more matter than others? What determined the scale and pattern of these early ripples? And could there be other quantum effects at play in the cosmos that we haven't yet discovered? These questions take us to the edge of our understanding, where quantum physics and cosmology meet in a dance of possibility and wonder. The story of quantum fluctuations is a reminder that the universe is full of surprises, even in its most fundamental aspects. From the tiniest particles to the largest structures, every piece of the cosmic puzzle is connected, weaving together a tapestry of space, time, and matter. And as we continue to explore these connections, we're reminded that the answers to the universe's biggest questions might just lie in the smallest details. In the early 20th century, Albert Einstein was grappling with a problem that would change the way we think about the universe. At the time, the prevailing belief was that the cosmos was static, eternal, and unchanging. But Einstein's own equations of general relativity suggested something entirely different, a universe that was either expanding or contracting. To reconcile this discrepancy, he introduced a mathematical fix, a term he called the cosmological constant. This constant represented a kind of repulsive force, counteracting gravity to keep the universe in balance. It was a bold, revolutionary idea, one that Einstein hoped would preserve the static model of the cosmos he and many others believed in. Yet, just over a decade later, Edwin Hubble's discovery of the expanding universe turned everything on its head. Hubble's observations showed that galaxies were moving away from each other, not standing still. Realizing his error, Einstein famously discarded the cosmological constant, calling it his greatest blunder. For decades, the idea was all but forgotten, relegated to the footnotes of scientific history. But the story didn't end there. Fast forward to the late 1990s, when astronomers made a startling discovery. The universe wasn't just expanding, it was accelerating. This revelation reignited interest in Einstein's long-abandoned constant. Could this repulsive force, once dismissed as a mistake, actually explain the mysterious push behind the universe's accelerating expansion? Suddenly, the cosmological constant was back in the spotlight, not as a blunder, but as a potential key to understanding dark energy. Today, Einstein's constant plays a central role in modern cosmology. It's often interpreted as the energy density of empty space itself, a subtle but pervasive force that drives the universe apart. In this context, the cosmological constant isn't a mistake. It's a profound insight, a mathematical expression of the very fabric of reality. It's a reminder that even the greatest minds can overlook the significance of their own ideas, only to have them rediscovered and reimagined by future generations. But the story of the cosmological constant is far from over. While it provides a compelling framework for dark energy, it also raises new questions. Why does the constant have the value it does? Is it truly constant, or could it change over time? And could it hold the key to solving the dark energy mystery? Or is there something even more fundamental at work? These are the questions that drive cosmologists today, as they explore the boundaries of our understanding and search for answers in the depths of space and time. Einstein's cosmological constant is more than just a scientific idea. It's a testament to the ever-evolving nature of discovery. What began as a theoretical fix has become one of the most important concepts in modern physics, shaping our understanding of the universe's past, present, and future. And as we continue to probe the mysteries of dark energy, we're reminded that sometimes the answers we seek are hidden in the very ideas we once thought we'd left behind. When it comes to measuring the vast distances of the universe, astronomers need tools that shine brightly and consistently, tools like Type Ia supernova. These cosmic explosions are more than just spectacular displays of energy. They're the universe's own measuring sticks, helping us map the cosmos with incredible precision. But what makes these supernovae so special? The answer lies in their remarkable consistency. Unlike other types of stellar explosions, Type Ia supernova all reach roughly the same peak brightness. This uniformity makes them perfect, standard candles, objects whose known brightness allows scientists to calculate their distance by measuring how dim they appear from Earth. The process works like this. Imagine you're standing in a dark room with a row of identical light bulbs placed at different distances. Even if you can't see the bulbs themselves, the farther away they are, the dimmer they'll look. Type Ia supernova act in the same way. By comparing their true brightness to how faint they appear in the night sky, astronomers can determine just how far away they are. This method has unlocked the ability to measure distances across billions of light years, giving us a clearer picture of the universe's vast scale. But Type Ia supernova don't just tell us how far things are, they also reveal how fast the universe is expanding. In the late 1990s, two teams of astronomers used these cosmic beacons to make a discovery that shook the foundations of cosmology. By studying distant supernova, they found that the universe's expansion wasn't slowing down, as many had expected, but accelerating. This groundbreaking revelation pointed to the existence of dark energy, the mysterious force driving galaxies apart at an ever-increasing rate. It was a discovery that earned the teams the Nobel Prize in Physics and forever changed our understanding of the cosmos. What makes Type Ia supernova even more fascinating is how they form. Unlike other supernova, which result from the collapse of massive stars, Type Ia explosions occur in binary star systems. When a dense white dwarf star siphons material from its companion, it eventually reaches a critical mass, triggering a runaway thermonuclear explosion. Because this process happens under very specific conditions, the resulting supernova are strikingly similar, making them reliable markers for measuring cosmic distances. Today, Type Ia supernova continue to play a crucial role in cosmology. They've helped refine the Hubble Constant, the rate at which the universe is expanding, and provided critical evidence for the accelerating expansion. But observing these cosmic beacons isn't easy. It requires cutting-edge telescopes, precise measurements, and a deep understanding of the physics behind these extraordinary events. In the next section, we'll dive into the tools and techniques astronomers use to study supernova, uncovering how they capture the light of these distant explosions and turn it into insights about the universe's past, present, and future. To truly understand the universe's expansion, we need tools that can see across unimaginable distances, capturing light that has traveled for billions of years. Enter the world's most powerful telescopes and observatories, our cosmic eyes, peering into the depths of space and time. From the iconic Hubble Space Telescope to the groundbreaking James Webb Space Telescope and the sprawling networks of ground-based observatories, these instruments are the backbone of modern cosmology, allowing us to witness the universe's grand story unfold. The Hubble Space Telescope, launched in 1990, has been a game-changer for astronomy. Orbiting high above Earth's atmosphere, Hubble avoids the distortions caused by air currents, delivering crystal-clear images of distant galaxies, supernova, and other celestial phenomena. It's responsible for some of the most iconic images in science, like the Hubble Deep Field, which revealed thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. But Hubble's contributions go far beyond stunning visuals. By measuring the light from distant supernova, it played a pivotal role in the discovery of dark energy, forever altering our understanding of the universe's fate. Then there's the James Webb Space Telescope, Hubble's successor and one of the most ambitious scientific projects ever undertaken. Launched in December 2021, Webb is designed to see even farther and fainter than Hubble, thanks to its massive gold-coated mirror and advanced infrared capabilities. Unlike Hubble, which observes primarily in visible light, Webb specializes in infrared wavelengths, allowing it to peer through cosmic dust and capture the faint glow of the earliest galaxies. This makes Webb an invaluable tool for studying the universe's infancy, offering glimpses of the first stars and galaxies that formed after the Big Bang. Already, Webb has delivered breathtaking images and data, shedding light on the processes that shaped the cosmos in its earliest moments. But space-based telescopes aren't the only players in this cosmic game. Ground-based observatories, equipped with massive mirrors and cutting-edge technology, also play a crucial role. Facilities like the Very Large Telescope in Chile and the Keck Observatory in Hawaii use adaptive optics, systems that adjust for atmospheric distortion in real time, to produce images nearly as sharp as those from space. These observatories are particularly well-suited for studying the large-scale structure of the universe, mapping the distribution of galaxies, and tracking the expansion of space itself. By combining data from space and ground-based instruments, astronomers can cross-check their findings, ensuring greater accuracy and depth in their observations. The technological advancements behind these telescopes are nothing short of remarkable. Adaptive optics, ultra-sensitive detectors, and sophisticated data processing algorithms have transformed our ability to study the cosmos. For example, modern telescopes can now capture light from objects so distant that their light has been stretched into the infrared spectrum, a phenomenon known as redshift. This allows us to observe galaxies as they existed billions of years ago, providing a window into the universe's past. Similarly, advancements in spectroscopy, the study of light's composition, enable scientists to analyze the chemical makeup of distant stars and galaxies, revealing clues about their formation and evolution. Yet with all these incredible tools, scientists face a daunting challenge: interpreting the vast amounts of data these telescopes produce. Every observation, from the faintest supernova to the most distant galaxy, adds to an ever-growing mountain of information. Sorting through this data requires not only advanced computing power, but also innovative techniques to extract meaningful insights. It's a bit like trying to piece together a jigsaw puzzle where the pieces are scattered across billions of light years and the picture keeps changing. But for astronomers, this challenge is also an opportunity, a chance to uncover new truths about the universe and refine our understanding of its history and future. As we continue to push the boundaries of observation, the next frontier lies in even more powerful telescopes and novel approaches to studying the cosmos. From the upcoming Vera C. Rubin Observatory, which will map the entire southern sky, to next-generation space telescopes designed to probe the nature of dark energy, the future of cosmology is brighter than ever. Each new discovery brings us closer to answering the profound questions at the heart of the cosmic push, questions that remind us just how much we have yet to learn about the universe we call home. The universe has a way of leaving behind clues, and one of its most profound messages comes in the form of a faint, uniform glow that fills the entire sky. This is the cosmic microwave background, or CMB, a relic of the Big Bang itself. Imagine it as the universe's very first photograph, taken just 380,000 years after its birth. At that moment, the cosmos had cooled enough for light to travel freely, and what we see today is the afterglow of that ancient light, stretched and faded over billions of years. It's a snapshot of the universe in its infancy, a time capsule that holds secrets about how everything began, But how did we come to discover this cosmic glow? In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large antenna in New Jersey when they stumbled upon a persistent background noise. At first, they thought it was interference, maybe static from nearby cities or even pigeon droppings on their equipment. But after ruling out every possible explanation, they realized they had found something extraordinary, the faint echo of the Big Bang itself. Their discovery earned them the Nobel Prize and provided the most compelling evidence yet for the theory of the Big Bang. The CMB wasn't just a whisper from the past, it was a roar, confirming that the universe had a beginning. The CMB isn't just a smooth, uniform glow, though. If you look closely, you'll find tiny variations in temperature fluctuations so small they are measured in millionths of a degree. These anisotropies, as they are called, are like cosmic fingerprints, revealing the seeds of structure that would later grow into galaxies, stars, and planets. Think of it like a pond on a calm day. The surface might look flat and smooth, but if you zoom in, you'll see ripples, tiny disturbances that hint at the forces shaping the water. In the same way, the CMB's anisotropies tell us about the early universe's density variations, areas where matter was slightly more or less concentrated. These fluctuations are the building blocks of everything we see today. What's truly remarkable is how well these anisotropies match the predictions of cosmic inflation, the theory that the universe underwent a rapid expansion in its earliest moments. Inflation stretched these tiny quantum fluctuations to cosmic scales, embedding them in the fabric of space-time. Over billions of years, gravity amplified these differences, pulling matter together to form the vast cosmic web of galaxies and galaxy clusters we observe today. The CMB is like a map of the universe's blueprint, showing us where the first stars and galaxies would eventually form. But the CMB isn't just a historical record, it's also a tool for understanding the universe's present and future. By studying its patterns, scientists can measure the universe's age, its rate of expansion, and even the amount of dark matter and dark energy it contains. It's a cosmic Rosetta Stone, helping us decode the mysteries of the cosmos. And as we continue to refine our measurements, the CMB promises to reveal even more about the forces that shape the universe and continue to shape its destiny. These tiny fluctuations in the CMB didn't just fade into the background, they set the stage for everything that followed. But how exactly did these ripples transform into the galaxies and stars we see today? That's the story we'll explore next as we delve into the cosmic web, the intricate network of galaxies that stretches across the universe, and the forces that brought it to life. If you could zoom out far enough to see the entire universe, you'd find it isn't just a random scattering of galaxies. Instead, it looks like an intricate, shimmering web, a vast network of galaxies, clusters, and vast, empty voids. This is the cosmic web, the universe's grand architecture, stretching across billions of light years. Picture it like a spider's silk, delicate yet strong, with threads of galaxies woven together by gravity and the invisible push of dark energy. It's a structure so immense, it defies imagination, and yet, it's shaped by forces we're only beginning to understand. At the heart of this web are the galaxies, clustered together in dense knots and filaments. These clusters, some containing thousands of galaxies, are the universe's metropolises, bustling with stars, planets, and cosmic activity. But between these clusters lie the voids, vast, empty regions that span hundreds of millions of light years. These voids aren't just gaps, they're the negative space that gives the web its structure, like the spaces between the threads of a spider's silk. Together, The clusters and voids form a pattern that looks almost alive, a living map of the cosmos. So, how did this web come to be? The story begins with the tiniest ripples in the early universe quantum fluctuations, stretched to cosmic scales by inflation. Over billions of years, gravity took hold, pulling matter into denser regions while leaving the voids behind. It's a bit like pouring water over a landscape. The water flows into the valleys, carving out rivers and lakes, while the higher ground remains dry. In the same way, gravity gathered matter into galaxies and clusters, creating the threads of the cosmic web. But as the universe expanded, dark energy began to play its part, stretching the space between these threads and shaping the voids into the vast, empty expanses we see today. What's fascinating is how this web connects everything. Galaxies aren't isolated islands, they're part of a larger network, linked by filaments of gas and dark matter. These filaments act like cosmic highways, guiding the flow of matter and energy across the universe. And within this web, gravity and dark energy are locked in a constant tug-of-war. Gravity pulls galaxies together, while dark energy pushes them apart, creating a delicate balance that shapes the web's structure. It's a dance that's been going on for billions of years, and it's still unfolding today. But here's the question: what happens next? As the universe continues to expand, will the cosmic web grow even more intricate, or will it begin to unravel? Could dark energy's relentless push eventually tear apart the filaments, leaving galaxies isolated in an ever-expanding void? Or will gravity find a way to hold the web together, preserving its structure even as the cosmos stretches? These are the mysteries that keep astronomers and cosmologists searching, probing the depths of space for clues about the universe's future. The cosmic web is more than just a map of the universe. It's a story of forces, balance, and evolution. It's a reminder that the cosmos is always in motion, shaped by the interplay of gravity and dark energy, and that even the largest structures in the universe have their roots in the smallest moments. As we continue to explore this vast network, we're not just uncovering the secrets of the cosmos, we're discovering our place within it. And with every new observation, every new insight, we're weaving our own thread into the fabric of the universe's grand story. As we journey deeper into the cosmos, we encounter a phenomenon that's like an ancient echo, a whisper from the universe's earliest moments. These are Baryon acoustic oscillations, or BAO, frozen sound waves imprinted on the fabric of the cosmos. Imagine the early universe as a seething cauldron of particles and energy, a place so hot and dense that sound waves could ripple through it like waves in a pond. These ripples, caused by the push and pull of gravity and radiation, left behind a signature, a pattern of peaks and troughs in the distribution of matter. Over billions of years, as the universe expanded and cooled, these ripples became frozen in time, etched into the large-scale structure of the cosmos. Today, they serve as a cosmic ruler, helping us measure the universe's vast distances and its rate of expansion. But how do these ancient ripples work as a measuring tool? Picture it like this: if you were to toss a stone into a pond, the ripples would spread out in circles, with a predictable distance between each wave crest. BAOs are similar. They create a consistent scale, a kind of cosmic yardstick. By mapping the distribution of galaxies and measuring the distance between these ripples, astronomers can calculate how far apart galaxies are and how much the universe has stretched since the BAOs were formed. It's a bit like using the rings of a tree to measure its age, except in this case, we're measuring the growth of the entire universe. the discovery of BAOs has been pivotal in confirming one of the most profound revelations in modern cosmology. The universe's expansion is accelerating. When astronomers began mapping these ripples in the late 1990s, they found that the distances between galaxies were larger than expected, suggesting that space itself was stretching faster over time. This observation aligned perfectly with the earlier findings from supernova studies, providing independent evidence for the existence of dark energy. BAOs didn't just confirm the universe's accelerating expansion, they reinforced the idea that dark energy is the dominant force shaping the cosmos. What's truly remarkable about BAOs is their precision. Unlike other methods of measuring cosmic distances, which rely on complex calibrations and assumptions, BAOs offer a direct, physics-based approach. They're a product of the universe's earliest moments, a snapshot of a time when everything was simpler, more uniform. This makes them an invaluable tool for probing the universe's history, from its fiery beginnings to its current state of accelerating expansion. By studying these frozen ripples, scientists can piece together the story of how the universe grew, evolved, and continues to change. Yet, measuring BAOs isn't without its challenges. The ripples are subtle, and mapping them requires observing millions of galaxies across vast stretches of space. It's a bit like trying to hear a whisper in a crowded room. You need the right tools and techniques to filter out the noise and focus on the signal. This is where cutting-edge telescopes and surveys come into play, capturing the faint traces of these ancient ripples and turning them into a road map of the cosmos. As we continue to refine our measurements, BAOs promise to reveal even more about the universe's past, present, and future. They're a testament to the power of sound, not just as a fleeting vibration, but as a force that has shaped the cosmos on the grandest scales. And as we listen to these ancient echoes, we're reminded that the universe's secrets are often hidden in its most subtle patterns, waiting to be uncovered by those who dare to look and listen closely. But what does it take to map these cosmic ripples with the precision needed to understand the universe's expansion? That's the challenge we'll explore next, as we dive into the tools and techniques astronomers used to measure the faint whispers of the early universe. Measuring the universe's expansion might sound straightforward, like tracking how fast a balloon inflates, but in reality, it's one of the most complex challenges in modern cosmology. The key number scientists are after is the Hubble Constant, the rate at which the universe is stretching. But here's the catch: depending on how you measure it, you might get different answers. It's as if two clocks, perfectly calibrated, started ticking at different speeds. This discrepancy, known as the Hubble tension, has become one of the most intriguing puzzles in science, and it's forcing us to rethink what we know about the cosmos. One way to measure the Hubble constant is by looking at the cosmic microwave background, the afterglow of the Big Bang. This ancient light carries imprints of the universe's earliest moments, and by analyzing its patterns, scientists can calculate how fast the cosmos has been expanding over its entire history. The result, a relatively slow and steady rate of expansion. But when astronomers measure the Hubble constant using nearby galaxies and supernova, they get a faster rate. It's like comparing a speedometer reading from the start of a road trip to one taken halfway through. They don't quite match up. So, what's causing this tension? One possibility is that our measurements are simply incomplete or flawed. Maybe there's a tiny error in how we calculate distances to supernova, or perhaps the cosmic microwave background isn't telling the whole story. But another, more exciting possibility is that this discrepancy points to something entirely new, a force or phenomenon we haven't yet discovered. Could there be an unknown ingredient in the cosmic recipe, one that's subtly altering the expansion rate? Or might our understanding of dark energy need an update? These questions aren't just academic, they're windows into the fundamental laws of the universe. Adding to the complexity is the fact that the universe isn't expanding at a constant rate everywhere. On small scales, gravity dominates, pulling galaxies together and creating local variations in the expansion rate. But on the largest scales, dark energy takes over, driving the universe apart faster and faster. This interplay between local and global effects makes it even harder to pin down a single, definitive value for the Hubble constant. It's like trying to measure the speed of a river while standing in the middle of swirling eddies and rapids. You need to account for every twist and turn. The stakes are high. If the Hubble tension is real, if the universe really is expanding faster now than it was in its infancy, it could mean that our current models of cosmology are missing a crucial piece. Maybe dark energy isn't constant, as we've assumed, but changes over time. Or perhaps there's an entirely new force at work, one that only becomes noticeable on cosmic scales. Either way, resolving this tension could lead to a revolution in our understanding of the universe, one that rewrites the rules of physics as we know them. But how do we solve this cosmic puzzle? The answer lies in more precise measurements, better tools, and innovative approaches to observing the universe. From next-generation telescopes to novel methods of mapping the cosmos, scientists are racing to close the gap between these conflicting measurements. And as we'll see in the next section, the solutions to this mystery might already be within reach, hidden in the light of distant stars and the echoes of the early universe. The Hubble tension isn't just a problem to solve, it's an opportunity to uncover something extraordinary, something that could change the way we see the cosmos forever. What if dark energy isn't the only answer to the universe's accelerating expansion? What if, instead of a mysterious force pushing galaxies apart, the problem lies in our understanding of gravity itself? This is the bold idea behind modified gravity theories, a fascinating alternative to the dark energy hypothesis. While dark energy has become the leading explanation for the universe's expansion, some scientists argue that tweaking our understanding of gravity might offer a simpler solution. After all, gravity is the force we thought we knew best, so why wouldn't it hold the key to this cosmic puzzle? One of the most well-known modified gravity theories is MIND, short for modified Newtonian dynamics. Proposed in the early 1980s by physicist Mordechai Milgrom, MIND suggests that Newton's laws of gravity, which work perfectly well on Earth and in our solar system, might need adjustment on much larger scales. Instead of invoking dark energy, MIND proposes that gravity behaves differently in regions where its pull is extremely weak, such as the outer edges of galaxies. In these low acceleration environments, gravity could become stronger than predicted by Newton's laws, potentially explaining why galaxies rotate faster than expected without the need for dark matter or dark energy. It's a radical idea, but one that has sparked decades of debate and exploration. MIND isn't the only modified gravity theory out there. Other approaches, like scalar tensor theories or FR gravity, propose adjustments to Einstein's theory of general relativity itself. These theories suggest that the fabric of space-time might behave differently on cosmic scales, creating effects that mimic the observed acceleration of the universe. For example, in some models, the strength of gravity could vary over time or across vast distances, subtly altering how galaxies move and interact. These ideas are mathematically complex, but they share a common goal: to explain the universe's expansion without relying on dark energy. But here's the challenge. Modified gravity theories face significant hurdles. For one, they often struggle to explain all the observations that dark energy accounts for so neatly. Take the cosmic microwave background, for instance. The intricate patterns in this ancient light are perfectly consistent with a universe dominated by dark energy, but they're harder to reconcile with modified gravity. Similarly, the large-scale structure of the universe, its web of galaxies and voids, seems to fit better with dark energy than with most modified gravity models. Critics argue that tweaking gravity might solve one problem but create others, leaving us with more questions than answers. Another major criticism is that modified gravity theories often require their own set of assumptions and new physics, making them no simpler than the dark energy hypothesis. In some cases, they even reintroduce the need for invisible components, like additional fields or particles, which defeats the purpose of avoiding dark energy in the first place. It's a bit like trying to fix a leaky pipe by replacing it with a more complicated system. It might work, but it's not necessarily the most elegant solution. Yet, despite these challenges, modified gravity theories remain an important part of the scientific conversation. They push us to question our assumptions, to explore whether the laws of physics we've relied on for centuries might need revision. And in doing so, they remind us that science is a process of constant discovery, where even the most well-established ideas are open to scrutiny. Could modified gravity eventually provide a better explanation for the universe's expansion, or will dark energy remain the dominant theory, its mysteries slowly unraveling as we probe deeper into the cosmos? The debate between modified gravity and dark energy is more than just an academic exercise. It's a window into how we understand the universe. It challenges us to think creatively, to consider possibilities beyond the mainstream, and to embrace the uncertainty that comes with exploring the unknown. Whether the answer lies in tweaking gravity or unraveling the nature of dark energy, one thing is certain: the journey to understand the cosmic push is far from over. And as we continue to explore these ideas, we're reminded that sometimes the most profound discoveries come from asking the simplest questions. What if our universe is just one of countless others, each with its own unique set of rules? This is the tantalizing idea behind the multiverse theory, a concept that takes us beyond the boundaries of our observable cosmos and into a sprawling cosmic landscape. Imagine a vast sea of bubble universes, each one a self-contained reality with its own physics, constants, and even dimensions. In some, gravity might be stronger, while in others, the speed of light could be different. Some universes might expand rapidly, while others could collapse in on themselves. It's a dizzying thought, but one that could help explain why our universe is the way it is, and why it's expanding at the rate we observe. At the heart of the multiverse theory is the idea that our universe isn't special, it's just one possibility among an infinite number. This concept often emerges from theories like cosmic inflation, which suggests that the rapid expansion of the early universe could have created pockets of space-time, each evolving independently. Picture a pot of boiling water. As bubbles form and rise to the surface, each one represents a separate universe with its own unique conditions. In this scenario, the laws of physics we take for granted, like the strength of gravity or the mass of an electron, might not be universal truths, but rather the result of random chance, determined by the conditions of our particular bubble. But what does this mean for universal expansion? If the multiverse exists, it's possible that each bubble universe has its own expansion rate, driven by its unique physical constants. In some universes, dark energy might dominate, causing runaway expansion. In others, gravity could reign supreme, leading to collapse. Our universe, with its delicate balance between these forces, might be just one outcome in an infinite array of possibilities. This idea could help explain why dark energy seems so finely tuned in our cosmos. It's not that the universe was designed this way, but rather that we happen to live in a universe where conditions allow for galaxies, stars, and life to exist. The multiverse theory also raises profound questions about the nature of reality. If there are countless universes out there, each with its own version of physics, what does that say about the uniqueness of our existence? Are we simply the product of a cosmic lottery, living in one of the rare universes where life is possible? Or could there be other forms of life, thriving in realities governed by entirely different laws? These questions push the boundaries of science and philosophy, challenging us to rethink our place in the cosmos. Yet, as fascinating as the multiverse theory is, it's important to note that it remains speculative. Unlike dark energy or the cosmic microwave background, the multiverse isn't something we can directly observe or test, at least not yet. Some critics argue that it's more of a philosophical idea than a scientific one, while others see it as a natural extension of our current understanding of physics. Either way, the multiverse concept serves as a reminder of how much we still have to learn about the universe, and how the answers to our biggest questions might lie far beyond the limits of what we can see. As we ponder the possibility of a multiverse, we're left with even more questions than answers. What does it mean for our understanding of reality if there are infinite universes out there? And how does this idea shape our search for meaning in the cosmos? These are the kinds of questions that take us from the realm of science into the territory of philosophy, where the boundaries of knowledge blur and the possibilities are as vast as the multiverse itself. And as we'll explore next, these questions don't just challenge our understanding of the universe, they challenge our understanding of ourselves. In the vast tapestry of the cosmos, there's an unseen force at work, one that doesn't emit light or interact with ordinary matter, yet shapes the universe in profound ways. This is dark matter, a mysterious substance that makes up about 27% of the universe's total mass energy content. While it's invisible to our telescopes, its presence is undeniable, revealed through its gravitational influence on the things we can see. Imagine dark matter as the cosmic scaffolding, an invisible framework that holds galaxies together and guides their movements across the universe. Without it, the cosmos as we know it simply wouldn't exist. So, how does dark matter shape the universe's structure? Picture a galaxy spinning like a pinwheel. The stars on the outer edges should, according to Newton's laws, move slower than those closer to the center. But observations show the opposite stars on the outskirts move just as fast, if not faster. This puzzling behavior can only be explained if there's something unseen adding extra mass to the galaxy, something that doesn't emit light but exerts a gravitational pull. That something is dark matter. It's like an invisible hand, holding galaxies together and preventing them from flying apart. On even larger scales, dark matter's influence becomes even more apparent. Galaxy clusters, collections of hundreds or even thousands of galaxies, are held together by dark matter's gravitational grip. These clusters are the universe's largest structures, and they wouldn't exist without dark matter binding them. Think of it as the cosmic glue, weaving galaxies into vast networks and creating the intricate web of the universe. Without dark matter, gravity alone wouldn't be strong enough to pull matter together on such massive scales. But dark matter's role goes beyond just holding galaxies together. It also plays a part in the universe's expansion. While dark energy drives the acceleration of that expansion, dark matter provides the gravitational counterbalance, slowing it down in localized regions. It's a delicate dance between these two forces. Dark energy pushes the cosmos apart on the grandest scales, while dark matter pulls it together on smaller scales. This interplay shapes the universe's evolution, from the formation of the first galaxies to the large-scale structure we see today. Despite its importance, dark matter remains one of the greatest mysteries in science. What is it made of? Is it a particle like the ones we know, or something entirely different? For decades, scientists have been searching for answers, using everything from underground detectors to particle colliders in the hunt for dark matter particles. One leading candidate is the WIMP, or weakly interacting massive particle, a hypothetical particle that could explain dark matter's properties. But so far, WIMP have eluded detection, leaving researchers to explore other possibilities, from actions to sterile neutrinos. And here's where things get even more intriguing. Could dark matter be connected to dark energy? While they seem like opposites, dark matter pulling, dark energy pushing, they might share a deeper link. Some theories suggest that dark matter and dark energy could be two sides of the same coin, different manifestations of a single underlying phenomenon. If true, this would revolutionize our understanding of the universe, revealing a hidden connection between the forces that shape its past, present, and future. The search for dark matter is more than just a quest for answers. It's a journey into the unknown, a chance to uncover the hidden threads that weave the fabric of the cosmos. And as we'll see next, this journey takes us even deeper into the interplay between dark matter and dark energy, two forces that hold the key to understanding the universe's ultimate fate. What happens when these titans collide, and how do their interactions shape the destiny of everything we see? The answers might just rewrite the story of the cosmos itself. In the grand cosmic dance, two invisible partners shape the fate of the universe, dark matter and dark energy. They are the yin and yang of the cosmos, each playing a vastly different role in how the universe evolves. Dark matter, with its gravitational pull, acts as the glue that holds galaxies and clusters together, while dark energy, with its relentless push, drives the universe apart at an accelerating pace. Together, they form a delicate balance, their opposing forces shaping the structure and destiny of everything we see. Picture dark matter as the cosmic architect. Its gravitational influence is what allows galaxies to form in the first place, drawing matter into dense clumps that eventually ignite into stars and planets. Without dark matter, the universe would be a far emptier place, with matter too thinly spread to coalesce into the structures we observe. It's like an invisible hand, sculpting the universe into its intricate web of galaxies and clusters. Yet, for all its importance, dark matter remains elusive, detectable only through its gravitational effects on the visible universe. Dark energy, on the other hand, is the cosmic rebel. Instead of pulling things together, it pushes them apart, stretching the fabric of space itself. Imagine blowing up a balloon with dots drawn on its surface. As the balloon expands, the dots move farther apart. That's dark energy at work, accelerating the expansion of the universe and creating vast voids between galaxies. Unlike dark matter, which binds structures together, dark energy drives them apart on the largest scales, shaping the universe's evolution over billions of years. Despite their opposing roles, dark matter and dark energy are both essential to the universe's story. Dark matter creates the scaffolding for galaxies and clusters, while dark energy determines the fate of the cosmos as a whole. But here's the intriguing question. Could these two forces be connected? Some scientists speculate that dark matter and dark energy might not be entirely separate entities, but rather two aspects of a single, deeper phenomenon. Perhaps they are different expressions of the same underlying physics, two sides of a cosmic coin that we're only beginning to understand. This idea isn't just speculative, it's backed by observations. For example, the distribution of dark matter in the universe seems to influence how dark energy behaves. In regions where dark matter is densely packed, its gravitational pull can counteract dark energy's push, slowing the expansion of space. But in the vast, empty voids where dark matter is sparse, dark energy dominates, accelerating the expansion even further. This interplay suggests a subtle connection between the two, hinting at a relationship that goes beyond their opposing effects. Could dark matter and dark energy be part of a larger cosmic puzzle, one that we're only beginning to piece together? Some theories propose that both forces might emerge from a single, unified framework, much like electricity and magnetism were once seen as separate phenomena before being united by the theory of electromagnetism. If true, this would be a monumental discovery, revealing a hidden symmetry in the universe's most fundamental forces. It would also mean that the story of dark matter and dark energy isn't just about their individual roles, but about how they interact to shape the cosmos. As we continue to explore these mysteries, we're reminded that the universe often hides its deepest secrets in plain sight. Dark matter and dark energy, though invisible, are the forces that define the universe's past, present, and future. They are the unseen architects of the cosmos, shaping its structure and driving its evolution. And while we may not yet understand their true nature, the search for answers is a journey that takes us to the very heart of existence itself. What we discover along the way might just change the way we see the universe and our place within it. In the late 1990s, astronomers made a discovery that turned our understanding of the universe upside down. For decades, scientists had assumed that the expansion of the cosmos, set in motion by the Big Bang, was gradually slowing down due to gravity's pull. But when two teams of researchers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, studied distant supernova, they found something astonishing. Instead of slowing, the universe's expansion was speeding up. It was as if the cosmos had hit the gas pedal, defying all expectations. This groundbreaking revelation earned the teams the Nobel Prize in Physics and forever changed how we see the universe. The key to this discovery lay in a special kind of stellar explosion, type Ia supernova. These cosmic events are like lighthouses in the night sky, shining with a predictable brightness that allows astronomers to measure vast distances across the universe. By observing how dim these supernovae appeared, the teams could calculate how far away they were, and in turn, how fast the universe was expanding. What they found was startling. The supernovae were dimmer than expected, meaning they were farther away than anticipated. The only explanation, the space between galaxies was stretching faster than ever before. This discovery didn't just rewrite the textbooks, it introduced a new chapter in cosmology. The idea that the universe's expansion could accelerate implied the existence of a mysterious force counteracting gravity's pull. This force, later dubbed dark energy, became one of the most profound mysteries in science. Suddenly, the universe wasn't just expanding, it was doing so at an ever-increasing rate, driven by something invisible and powerful. It was a humbling reminder of how much we still don't know about the cosmos. The implications of this finding were immense. It suggested that the universe's fate wasn't just a slow fade into darkness, as many had assumed, but something far more dramatic. If dark energy continued to dominate, the cosmos could stretch endlessly, leaving galaxies isolated in a vast, cold void. This wasn't just a scientific breakthrough, it was a philosophical one, challenging our assumptions about the nature of reality itself. But how did this discovery come about? The team's work was a triumph of collaboration and innovation, combining cutting-edge technology with meticulous observation. Using telescopes around the world, they painstakingly collected data on distant supernovae, analyzing their light to uncover the universe's secrets. It was a race against time and uncertainty, but their perseverance paid off, unveiling a truth that reshaped our understanding of the cosmos. This revelation also sparked new questions. What exactly is dark energy? Is it a property of space itself, or something more exotic? And what does its dominance mean for the future of the universe? These are the puzzles that scientists are still grappling with today, as they peer deeper into the cosmos, searching for answers hidden in the light of distant stars. The discovery of the accelerating universe wasn't just a moment in science, it was a turning point, a reminder that the cosmos is full of surprises, waiting to be uncovered. As we explore the implications of this acceleration, we're reminded that the universe's story is still being written. Each new discovery brings us closer to understanding the forces that shape our reality, from the smallest particles to the largest structures. And as we'll see next, the consequences of this cosmic push are as profound as they are mysterious, shaping the destiny of everything we know. The universe's accelerating expansion isn't just a scientific curiosity, it's a force that will reshape everything we know about the cosmos. As dark energy continues to push galaxies apart, the very fabric of the universe is being stretched, creating a future that's both awe-inspiring and unsettling. Imagine a cosmos where galaxies drift farther and farther away, their light fading into the void, leaving behind a sky that grows darker with every passing eon. This isn't a distant possibility, it's the trajectory we're already on, and it has profound implications for the future of the universe. One of the most immediate effects of this accelerated expansion is on the formation of new stars. Stars are born from clouds of gas and dust, regions where gravity pulls matter together until it ignites in a burst of light and heat. But as dark energy stretches the universe, it's also pulling these clouds apart, making it harder for gravity to do its work. Over time, the process of star formation could slow to a crawl, leaving the universe with fewer and fewer new stars to light up the darkness. It's like a cosmic dimmer switch, gradually turning down the brightness of the cosmos. Galaxies, too, will feel the effects. In the near term, gravity will continue to hold them together, but as the expansion accelerates, even the strongest gravitational bonds may not be enough. Galaxies on the outskirts of clusters could be torn away, drifting into the void as isolated islands in an ever-expanding sea. Over billions of years, the cosmic web, the intricate network of galaxies and clusters, could begin to unravel, leaving behind a universe that's sparse, fragmented, and eerily quiet. But what does this mean for life? Could civilizations like ours survive in a universe that's growing colder and more isolated? The answer is far from clear. On one hand, the accelerating expansion could make it harder for life to thrive, as galaxies grow more distant and resources become scarcer. On the other hand, some scientists speculate that advanced civilizations might find ways to adapt, harnessing the energy of black holes or even manipulating the fabric of space itself. It's a question that blurs the line between science and speculation, challenging us to think about the resilience of life in the face of cosmic change. The ultimate fate of the universe is equally uncertain. Will dark energy continue to dominate, driving the cosmos toward a cold, dark end, or could there be a twist in the story, a force or phenomenon we haven't yet discovered that could alter the trajectory of expansion? These are the questions that keep cosmologists awake at night as they peer into the depths of space, searching for clues about the universe's destiny. As we grapple with these profound implications, we're reminded that the universe's story is still unfolding. The accelerating expansion isn't just a scientific fact, it's a narrative that shapes how we see ourselves and our place in the cosmos. And as we'll explore next, this narrative isn't just about physics and astronomy, it's also a deeply philosophical journey, one that challenges us to think about existence, time, and the nature of reality itself. What does it mean to live in a universe that's constantly changing, constantly growing? The answers might just redefine how we understand everything. The accelerating expansion of the universe isn't just a scientific phenomenon, it's a mirror that reflects profound questions about who we are and our place in the cosmos. As we gaze into the infinite expanse, it's impossible not to feel a mix of awe and humility. The sheer scale of the universe, with its billions of galaxies and trillions of stars, can make humanity seem vanishingly small, like a single grain of sand on an endless beach. And yet, here we are, on a tiny planet, daring to ask questions about the nature of existence itself. What does it mean to live in a universe that's not only expanding but doing so at an ever-increasing pace? How do we find meaning in a cosmos that seems indifferent to our presence? These are questions that have echoed through human history, from the earliest philosophers to modern-day thinkers. The vastness of the universe has always sparked a sense of wonder, but it also challenges us to confront our own insignificance. In the face of such enormity, it's natural to feel small, even insignificant. But there's another way to look at it. Our ability to ponder these questions, to study the cosmos and unravel its mysteries, is itself a remarkable achievement. In a universe that's constantly changing, we are the rare beings capable of observing, understanding, and even shaping our own destiny. The accelerating expansion adds a new layer to this philosophical puzzle. As galaxies drift farther apart and the universe grows colder and darker, what becomes of our connection to the cosmos? Will future generations look up at a night sky that's far emptier than ours, with fewer stars to guide their imaginations? And if the universe is destined to fade into darkness, what does that mean for the human desire to explore, to create, and to leave a mark on existence? These are not just scientific questions, they're deeply human ones, touching on our longing for purpose and our search for meaning. Yet, even as we grapple with these existential questions, there's a sense of hope. The same universe that seems indifferent to us has also given us the tools to explore it. Through science, art, and philosophy, we've built a bridge between the finite and the infinite, between the fleeting nature of our lives and the timeless expanse of the cosmos. In that sense, the universe's expansion isn't just a force that pushes galaxies apart. It's an invitation to stretch our own understanding, to reach beyond what we know and imagine what could be. These ideas don't just resonate in the realm of philosophy, they've also shaped how we see ourselves in the broader context of culture and history. From ancient myths to modern literature, the cosmos has always been a source of inspiration, a canvas for our hopes, fears, and dreams. And as we'll see next, the way we interpret the universe's expansion has left an indelible mark on our collective imagination, influencing everything from art to religion to the stories we tell about our place in the grand scheme of things. The cosmos isn't just something we observe, it's something we live in, something that shapes who we are and who we might become. The mysteries of the universe's expansion aren't just confined to scientific journals or telescopes, they've also found their way into the heart of popular culture. From blockbuster movies to best-selling novels, the idea of an ever-expanding cosmos has captured the imagination of storytellers and artists, weaving the grandeur of space into the fabric of our everyday lives. Take Christopher Nolan's Interstellar, for example. The film doesn't just dazzle with stunning visuals of black holes and distant galaxies. It uses the concept of cosmic expansion as a backdrop to explore profound themes of time, love, and survival. Through the lens of a father's journey across the stars, the movie invites us to grapple with the vastness of space and the fragility of human existence. It's a reminder that the universe's mysteries aren't just scientific, they're deeply personal too. Then there's Contact, based on Carl Sagan's novel, which takes a different approach. Instead of focusing on the physical expansion of the universe, it delves into the philosophical implications of our place within it. The story follows Dr. Ellie Arroway as she makes first contact with an alien civilization, sparking questions about humanity's role in a cosmos that seems both infinite and indifferent. These narratives don't just entertain, they spark curiosity, encouraging audiences to think about the bigger questions that science is still trying to answer. Why are we here? Are we alone? And what does it mean to live in a universe that's constantly stretching and evolving? Art, too, has embraced the theme of cosmic expansion. From abstract paintings inspired by the Hubble Deep Field to immersive installations that simulate the vastness of space, artists have found ways to translate the awe of the cosmos into something tangible. These works don't just reflect the beauty of the universe, they also serve as a bridge between science and the public, making complex ideas accessible and relatable. When we see a swirling galaxy rendered in paint or light, it's not just a representation of space, it's an invitation to wonder, to explore, and to feel connected to something far greater than ourselves. These cultural portrayals do more than entertain, they shape how we think about the universe. They turn abstract concepts like dark energy and cosmic expansion into stories we can relate to, sparking curiosity and inspiring the next generation of scientists, artists, and dreamers. They remind us that the cosmos isn't just a collection of stars and galaxies. It's a canvas for our imagination, a place where science and storytelling collide. But while movies and art help us imagine the universe's mysteries, they also point us toward the next frontier, the future of cosmic exploration, what lies ahead as we continue to push the boundaries of our knowledge. From cutting-edge telescopes to ambitious missions beyond our solar system, humanity's quest to understand the cosmos is far from over. And as we'll see next, the tools and technologies we're developing today could unlock answers to questions we haven't even thought to ask yet. The journey into the unknown is just beginning, and the universe's secrets are waiting to be discovered. As we peer deeper into the cosmos, the tools we use to explore its mysteries are becoming more advanced than ever before. The future of cosmic exploration is brimming with groundbreaking missions and cutting-edge technologies, each designed to unravel the secrets of universal expansion. Among these, the Euclid Space Telescope stands out as a beacon of hope for cosmologists. Launched by the European Space Agency, Euclid is on a mission to map the distribution of dark matter and dark energy across the universe with unprecedented precision. By observing billions of galaxies, Euclid aims to uncover the subtle ways these invisible forces shape the cosmos, offering clues that could transform our understanding of the universe's past, present, and future. But Euclid isn't working alone. On Earth, the Vera C. Rubin Observatory is poised to revolutionize our view of the night sky. Nestled in the mountains of Chile, this state-of-the-art facility will conduct the Legacy Survey of Space and Time, a decade-long project that will capture the most detailed map of the universe ever created. Using its massive telescope and advanced camera, the Rubin Observatory will track the movements of galaxies, detect faint supernova, and even identify transient events like asteroid collisions. Together, Euclid and Rubin represent a new era of collaboration between space and ground-based observatories, combining their strengths to tackle some of the most pressing questions in cosmology. These missions aren't just about gathering data, they're about solving puzzles. One of the biggest mysteries they aim to address is the nature of dark energy. Is it a constant force, as Einstein's cosmological constant suggests, or does it change over time? Could it even be connected to dark matter in ways we haven't yet imagined? By mapping the universe's expansion with unparalleled accuracy, these projects could provide the answers we've been searching for, shedding light on the forces that drive the cosmos. And then there's the potential for entirely new discoveries. What if dark energy isn't what we think it is? Could there be other, unknown forces at play, influencing the universe's expansion in ways we've yet to detect? The data collected by Euclid and Rubin could reveal unexpected patterns, anomalies that challenge our current models and open the door to entirely new theories. It's a thrilling prospect, one that reminds us how much we still have to learn about the universe, but these missions are just the beginning. As we develop even more advanced technologies, like next-generation space telescopes and gravitational wave detectors, we're pushing the boundaries of what's possible. Each new tool brings us closer to understanding the universe's most profound mysteries, from the nature of dark matter to the ultimate fate of the cosmos. And as we continue to explore, we're reminded that the journey of discovery is never-ending. Every answer we find leads to new questions, propelling us forward in our quest to understand the vast, beautiful, and ever-expanding universe. As we look ahead to these exciting developments, it's worth pausing to reflect on how far we've come. From the first observations of distant galaxies to the discovery of dark energy, each step has brought us closer to understanding the cosmic push. And as we'll see next, this journey isn't just about science, it's about the human spirit, our relentless curiosity, and our drive to explore the unknown. What lies ahead is more than just new discoveries. It's a deeper connection to the universe and our place within it. From the fiery birth of the universe in the Big Bang to the invisible push of dark energy shaping its destiny, our journey through the cosmos has been nothing short of extraordinary. We've traced the echoes of creation in the cosmic microwave background, marveled at the delicate dance between dark matter and dark energy, and pondered the ultimate fate of everything we know. Along the way, we've uncovered secrets that have reshaped our understanding of reality, and yet, for every question answered, new mysteries have emerged. What began as a quest to understand the stars has become a profound exploration of existence itself. Think about how far we've come. Just over a century ago, Edwin Hubble's discovery of the expanding universe shattered the notion of a static cosmos, opening the door to a new era of cosmology. Since then, we've mapped the cosmic web, deciphered the whispers of ancient supernova, and peered into the depths of space with tools that once seemed like science fiction. Each discovery has been a testament to human curiosity and ingenuity, a reminder that even in the face of the infinite, we're driven to seek answers. Yet, as much as we've learned, the universe remains full of enigmas. What exactly is dark energy? How did the Big Bang happen? And what lies beyond the observable universe? These questions remind us that the cosmos is a puzzle still being pieced together, but this journey isn't just about science, it's about perspective. The vastness of the universe can make our lives here on Earth feel fleeting, even insignificant. And yet, it's precisely this scale that underscores the beauty of our existence. We are the universe observing itself, asking questions and seeking meaning. In a cosmos that spans billions of light years, the fact that we can even begin to understand its workings is nothing short of miraculous. It's a humbling thought, but also an inspiring one. Every telescope we build, every equation we solve, every star we map is a step closer to unraveling the grand story of existence. So, what's next? The future of cosmic exploration is brighter than ever. With missions like Euclid and the Vera C, Rubin Observatory on the horizon, we're poised to uncover even more about the forces shaping our universe. Will we finally decode the nature of dark energy? Could we discover new dimensions or even other universes? The possibilities are as limitless as the cosmos itself, and as we continue to explore, we're not just uncovering the secrets of the universe, we're also learning more about ourselves. What does it mean to live in a universe that's constantly expanding, constantly changing? What role do we play in this grand cosmic story? As we bring this journey to a close, let's take a moment to reflect on what we've learned and what's still out there waiting to be discovered. The universe is a place of endless wonder, a tapestry of forces and phenomena that challenge our understanding and ignite our imagination. And while we may never have all the answers, the pursuit of knowledge is a journey worth taking. After all, the cosmos isn't just something we observe, it's something we're a part of, a story we're helping to write with every step we take into the unknown. What will we discover next? Only time and the stars will tell. From the explosive birth of the universe in the Big Bang to the invisible forces shaping its destiny, our journey through the cosmos has been nothing short of extraordinary. We've explored the echoes of creation in the cosmic microwave background, marveled at the delicate balance between dark matter and dark energy, and pondered the ultimate fate of everything we know. Along the way, we've uncovered secrets that have reshaped our understanding of reality, and yet, for every question answered, new mysteries have emerged. What began as a quest to understand the stars has become a profound exploration of existence itself. The universe's expansion isn't just a scientific phenomenon, it's a story about forces we can't see but whose effects are everywhere. Dark energy, that mysterious push driving galaxies apart, challenges everything we thought we knew about the cosmos. Coupled with dark matter's invisible scaffolding, these forces shape the universe on the grandest scales, from the tiniest ripples in the early universe to the sprawling cosmic web we see today. And while we've made incredible strides in understanding these phenomena, they remain some of the greatest puzzles in science. But this journey isn't just about the universe, it's about us. Humanity's quest to unravel these mysteries is a testament to our curiosity and ingenuity. From Edwin Hubble's groundbreaking discovery of the expanding universe to the Nobel Prize-winning revelation of dark energy, each step forward has been driven by our insatiable desire to explore the unknown. And with every discovery, we're reminded of how much we still have to learn. What exactly is dark energy? How did the Big Bang happen? And what lies beyond the observable universe? These questions keep us looking up at the stars, searching for answers. The cosmos is vast, awe-inspiring, and humbling. It stretches across billions of light years, filled with galaxies, stars, and planets, each a piece of the cosmic puzzle. Yet, in the face of such enormity, we've found ways to connect with it, to understand it, and even to feel a part of it. The universe's mysteries aren't just scientific. They're deeply personal, sparking wonder and reflection about our place in the grand scheme of things. As Carl Sagan once said, "Somewhere, something incredible is waiting to be known." This sentiment captures the heart of our cosmic journey. The universe is full of secrets, waiting to be uncovered by those who dare to ask questions and seek answers. Whether you're a seasoned space enthusiast or just beginning to explore the wonders of the cosmos, there's always more to discover. So, let's keep looking up, keep wondering, and keep exploring. What do you think about the universe's expansion and the mysteries of dark energy? Share your thoughts in the comments below. I'd love to hear your perspective. And if you enjoyed this cosmic adventure, don't forget to subscribe for more journeys into the unknown. Together, let's continue unraveling the secrets of the cosmos, one discovery at a time. After all, the universe's story is far from over, and neither is ours.